Hi gents, this is going to be a really important video. We're not just going to do a sample paper, we're also going to learn a few things along the way. Stuff that we were going to tie up whenever we were back in school, but of course, things being how they are, we'll just have to do it here. So what I would like you to do is I would like you to just take this one particularly seriously. Do actually go through all of the video, because not just the start. There will be bits that you'll be learning in between questions. So this, just to explain, is the Educate.ie sample papers. They're in the file section that I have that I've uploaded onto Microsoft Teams. I've already done questions 1 to 3 for you, and now we're going to have a look at a question 4 all the way to 6. So that'll be the end of the short questions. So question 4 starts off with a proof by induction. It's an inequality proof by induction. I'll be totally honest with you, I've said this to you before. It's one of 3 types. This type came up last year. I'm not actually going to waste time doing this one. I think it's extremely unlikely to come up. You can have a look at it inside your book and try it yourself, and if you really want to know, just email me. But for the time that it would take to do that particular question, I don't actually think that there's good benefit from it. You know how to start off, at least, so that you can get 7 out of 10 marks on that particular one. In the very unlikely event that it comes up, try for n equals, in this case typically it's n equals 1, in this case it's n equals 7, excuse me. Try for, just assume for n equals k, and then try for n equals k plus 1, and go from there. You should be able to get it. Okay, so what we'll actually start with is question 4b. It's a geometric series, as you see here. For a geometric series, b going to b or squared, going to b or to the power 4. Write down what Sn is. So this is a little bit unusual. It goes b or squared, b or to the 4. Just remember, if it's geometric, you are multiplying by something each time. So what do you have to multiply by to go from there to there? And obviously you'd be multiplying by or squared. And we just check, is that true here? It is. So we know that it's geometric, and we know what we're multiplying by each time. Now, tiny bit tricky here. They're asking us to write down Sn. Our Sn formula for geometric is a times 1 minus or to the n over 1 minus or, as in the tables book. What does a mean here? A means the first in the sequence, and or in this case means what are you multiplying by. So they've mixed things up a little bit here, because you're multiplying by or squared. So or is or squared. You know what? It's just much easier. Instead, if you call the formula this thing here, okay, we'll just capitalize it. It just makes it a little bit more clear as to what's going on. Capital A means first term in your sequence, and capital or means what you are multiplying by, the common ratio. So if we write it like that, what we can say is that A, first in the sequence, is B, and capital or, meaning what we're multiplying by, is or squared. So in this case, Sn, for that first thing, Sn is equal to capital A, so that's B, times 1 minus, and it's or to the power of n, capital or to the power of n. Capital or is or squared, so it's or squared to the power of n, all over 1 minus or, capital or that is or squared. So that is what we have here. They probably want us to do, I would imagine, is to say that Sn, maybe I'll write it just over here to give us some space. Sn in this case is equal to b times 1 minus, this one you should know yourself by the rules of logs. It says a to the m all to the n is a to the mn. So that's going to be or to the 2n. 1 minus or squared. Okay, so we have our answer there. That is for our first one that we have. Second one is for the geometric sequence a or squared. Write down s of 2n. So actually this one is extremely it is the definition of what a geometric series would be. A a or squared, etc. I mean, that's what we actually use for a geometric sequence. In this case, if we continue to call it capital A is just A and capital OR is just OR. So we can just take that immediately from the tables book. S of n is equal to A times 1 minus OR to the n over 1 minus OR. That's the definition, but that isn't quite what they asked. They asked us to find S of 2n. So if we just write that out again, that means when we place n into the function, you can think of it just like a function. So S of 2n, instead of n, we're just putting in 2n. So it's going to be A times 1 minus OR instead of n, now 2n, and it's over 1 minus OR. There we go. And it's then asking us to equate those two things that we just got, okay? Equate those things together, and apparently OR is going to be equal to B over A minus 1. So let's try that. I'm actually going to do that maybe over to the side. They want us to show that Sn from the original B valued one, if we let it equal to S of 2n for the A valued one, so that is to say that B times 1 minus OR to the 2n over 1 minus OR squared is equal to A times 1 minus OR to the 2n over 1 minus OR. Now I'd encourage you at this stage maybe to try and have a shot at this one yourself, because there is a nice little trick to it again, and it's all about you being comfortable with those little tricks, finding like a nice little shortcut into the path. So have a shot at it yourself, and here comes the answer. Okay, first thing that you might want to do is you might want to divide both sides by 1 minus OR to the 2n. So we just get B over 1 minus OR squared is equal to A times 1, sorry, the whole point was that we divided by that. So it's just A over 1 minus OR. Okay, here's what the real trick is. The real trick is to notice about B over 1 minus OR squared, that 1 minus OR squared is a particular thing. So maybe if you didn't get it from there, still pause it here, you still have a chance to get this right. You can write that in a particular way. That's going to be helpful. And here it is. It is, of course, the difference of two squares. So it's 1 minus OR times 1 plus OR. That's equal to A over 1 minus OR. So now when you multiply both sides by 1 minus OR, you'll just get B times 1 plus OR, and you'll just get A. So now we will have B equals A times 1 plus OR. And what was the actual thing we were looking for? We're trying to get what is OR in this case. Okay, well, divide both sides by A. And there we have it. Okay, that was that question. Tough question, as you can see. But all of these are challenging, and you know what? It's good to have some challenging questions in there. Okay. Right, question 5. We're actually going to be doing quite a bit of learning inside of this. This is not necessarily all stuff that we have done, especially when we see here bijective. We will get to that in just a second, but that is not stuff that we have done together. So we're going to be learning that over to the side, and then we'll come back to the actual question, try and answer it. So let's start. We can actually get the first few things. Shouldn't be a problem. The function f of x or y, another way to say it, is equal to a to the x is shown. If that is true, find a. Okay, if this is on the curve, so you know that we just make that x, we make that thing y. So instead of having y equals a to the power of x, we can instead say 1/3 is equal to a to the minus 1. So a to the minus 1, you should already know, is 1 over a. So it follows that a is 3. So we now know what the function is. The function is f of x is equal to 3 to the power of x. B part 1. Find the coordinates of B, which is the y-intercept. What do they mean by the y-intercept? Where something crosses the y-axis. And you can always be sure, you know, if something crossed the y-axis there, you don't necessarily know what the y value here is. It's 2 point something or other. But you do know the x value. The x value is 0 something. So whenever you see something crossing the y-axis, that implies that x is 0. So we have that y, or f of x, is 3 to the power of x, but we're told that x is 0. So y is going to be 3 to the power of 0. So y is going to be 1. Find the coordinates, x value 0, y value 1. I mean, it kind of looked like that anyway. So as they put it maybe slightly off, just to try and, you know, make you think maybe it's 1 point something or something along those lines. Okay, we get to our question here that we don't know much of. So I'm gonna try and teach you this here. What is it to be bijective? So there are 3 things that we need to know. I'll just move over to the side here and we'll just learn these off. Three terms that we're going to learn here. I'm going to start with injective, then we'll look at surjective, and finally we'll look at bijective. I'll do that in a second. Okay. When you have a function, there are certain things that you can put into it and certain things that you can get out of it. Okay, so let's have a look at just our inputs and our outputs. Well, first of all, we need to get a function to have a talk about this. So we'll just make one up, and we'll say we'll get the function f of x or y is equal to 7x plus 3. Okay. In terms of our input, can we put anything that we want into that? You know, is there any value of x that just we could not put in there? And the answer is no. We would be able to put any value that we wanted in there. Could we get any value out? You know, is it possible here to get every value out? The answer is it is. Yeah, it's possible to get anything out. Depending on what we put in, we can get anything out. Now, what do I mean here? Let's look at some examples where, for instance, you can't just put everything into the function. I'll give you an example. 1 over x. There's a specific value here of x that you can't put in. Hopefully you know what it is. And you can't put in 0 in here. Okay, so this would be a case where you can't actually just place any number that you want in. And if we were to just change it around, like x plus 3, now there's another value that you can't put into this one, and it is of course minus 3. Okay, obviously you can never divide by 0, so that would be an example of something that can't have just anything go into it. If you want an example of something that can't have you know, anything come out of it, this function here, you won't get a negative answer out of this. Okay, we're not talking about putting in a complex number. Obviously, if you put in a complex number, but if you put in any real number, you will only get positive or 0 back out. You won't get a negative number out of this. So that's the first thing, is just to figure out that there are sometimes limits in not the limit sense, but there are restrictions on what you can put in, and there are sometimes restrictions on what you can put out. Okay. If we were to graph, maybe use some of these things here. So we'll graph x squared. What does that thing look like? Okay, that'll look something like that. And we'll just maybe get our little definition here of what's injective. And maybe take another function. We'll take, this is y equals x squared. We'll take y equals x. That would be that line there, except hopefully going through the origin. That's good enough for me. Okay, injective means every y value, or another word for y value is output. Every y value has at most one x value. Okay. What do I mean by that? If we have a look at our function over on the right hand side, y equals x, every y value, so if I pick a y value, we'll just change colors. If I pick this y value here, is there an associated x value? Well, there is. If we put in this x value in there, we get out that y value there. Okay, as in if you put in, I don't know, 4, you'll get out 4. Okay, so that's what you have going on there. And if you were to take a y value of, let's say, 5, the point is this. The point is that if you were to take 5, there is one associated x value, and it is 5 itself right there. But there's no other x value that's going to give that to you. If you take a look at our other example, instead of 5 here, just imagine that I picked 9 or something like that. That'd be a bit better. If instead you go to a y value of 9 over here, there is an x value, there is an x value associated with that, and it is 3. But there is another x value that's associated with it, and that's -3. Okay, so injective says that every y value, if a function is injective, it means that every y value has at most one x value. That is to say, at most, that means that it either has one value or no value whatsoever. Okay, and it is fine to have no x value associated with it. But if it has more than one x value associated, in this case 3 and -3, those are 2 x values that will give you that y value. So this thing here, this thing is not injective, whereas this one is injective. Okay, that's the difference between it. Every y value has at most one x value. If we go to surjective, its definition. Surjective is, maybe we'll write it a little bit above. This means every y value has at least one x value. Okay, I should have said just on injective, one way that you can check whether a function is injective if you've got it drawn out. If you draw a horizontal line, if you draw a line across, if it hits the graph in 2 places, that means that there are 2 x values therefore associated with that one y value. I've lost my function, but it looks something like that. Whereas over here, if we drew a horizontal line, it's only going to hit our graph once. Okay, it's fine to draw the graph and not hit it at all. That would be fine. You'd still be injective if that's the case. But if there's anywhere where you can draw the graph and hit the function twice, then it is not injective. Okay, coming back to surjective, every y value has at least one x value. So for instance, 9 here has at least one x value. It happens to have 2, but 2 is at least 1. Okay, it's more than 1, at least 1, 1, 2, 3, etc. So -9, that's fine. Okay, whereas if we were to go to 0, there is an associated value. If you place in 0, you'll get out 0. That is having one value. But if you go to -1, okay, there is no associated x value. So again, it is a horizontal line test, as it's called. In this case, what you want to do in order to be surjective, it just has to hit the graph. There has to be somewhere where it'll hit the graph. In this case, it doesn't. Okay, so this thing is not surjective. Not every y value is used up. Okay, -1 does not, there's no x value. There's no x value that you can put in that would give you an output of -1. Okay, whereas over here, is every y value used up? So for instance, is there an associated x value for an associated x value for when y is -1? And there is. Okay, if you were to draw a horizontal line, no matter where you drew it, you will always end up hitting the graph. Okay, hits it there, hits it there, hits it there. There's nowhere where you can draw a horizontal line and not hit the graph. Okay, so this thing is also surjective. Okay, what were we asked? We were asked this thing called bijective. Well, bijective is very simple. If you are both injective and surjective, you're bijective. You have to be both things. If you're injective but not surjective, you are not bijective. Bijective means that you're both things. So this thing is bijective because it's both injective and surjective, whereas this one is not bijective. Okay, that is what it means, but things can get a little bit more complicated, okay, as always. Haven't seen them ask this too much. In fact, I don't know if they've ever asked this, but I am just going to make a point of it, okay? What we were really talking about there was we were talking about if I put in real numbers and I look at real numbers coming back out, okay? But if we just have a look at this function over on the left-hand side, y equals x squared, there is a way that they might call it. They might say, looking at all real inputs going in and just looking at positive real numbers on the way out. So if we just go back to our little definition there, okay, all we're going to put in is we're just going to put in real numbers, any real number, and then we will have a look and we will only consider positive outputs. So let's see, what does that mean? So in this case, is it injective? Okay, we're only going to put in x values, so you can kind of think of it as x going to y. We're only going to put in inputs which are, we can put in any input, in fact. Okay, so will every y value have at most one x value? So we can only consider the outputs that are positive real numbers, like for instance 9. Okay, so 9 is fine. Will every y value have at most one x value? No, 9 still has 2 of them. Okay, 9 doesn't have at most one x value, so it's not injective. But have a look at this surjective. Is every y value covered? Now look what they can do. They can specify that the only y values that you look at are the positive y values. Okay, I'm going to take all the positive y values. Do all the positive y values here, do all of them have at least one x value? Well, if you perform the test, and if you're only testing on the positive values, every time you draw the line, you will definitely end up hitting the curve. So actually in this case, if they specified it in this way, if they said only looking at all the positive outputs, it would mean that you were dealing with a surjective function. It would still not be bijective because you need both things in order for that to be the case. But there you go. That's a real tricky one that you have to consider. And there's a particularly good question. It's again from the Educate papers. It's their sample 4. It's the 4th sample. It's paper 1, and I think I have it here for you. Yeah, it's question 5. That's something that I want you to do here. Okay, that's a good one to do. They've got a few different things here. Sometimes they draw them, sometimes they don't. They want you to just tick, are you dealing with an injective, surjective, bijective function? Okay, and that's one where I'll actually do a separate video just on that one particular question. I would take that as my homework, because that's a really important one to know. Let's have a little look at this question here. Is f of x a bijective function for OR to OR? So what they're saying is we can put in any number, we can get out any number. That's all that means right there. So remember, to be bijective, you must be both injective and surjective. So what does injective mean? Every y value has at most one x value. So if you were to do a horizontal line, you don't want to hit the graph more than once. And you won't hit the graph more than once. Okay, you will only hit the graph once up here, and you won't hit it there. But the point is that you shouldn't hit it twice. Okay, so is this thing injective? It is injective. Is it surjective? Is every y value used up? Well, if it said to OR plus, that just means looking at all the positive y values. Every y value does get used up. Every y value will have one x value associated with it, but it doesn't say that. It instead says, you know, you have to look at every single y value, and no, all these y values here are not included. If you have y equals 3 to the x, there is no x value that you can put in to get a negative number. If you put in -1 or something like that, you get 3 to the power of -1, you just get a third. In fact, that is point A. It is not going to be a negative number. So this thing here is not surjective, and I would say therefore not bijective. Bijective. Does ask for a reason. Well, we've given the reason that it is injective and not surjective, but I might say this one, it fails the horizontal line test. You can also say, you know, 3 to the power of x is never going to equal to -1. Sorry, screen moving on me. You can also say that. So you've got loads of things that you can say on there. Okay, the C part asks you to draw log of x to the base a. We know that a was 3, I think it was, yeah. So this really is just a bit of calculator work. Y is equal to log of x to the base 3. Just make out a grid is what I'm going to suggest to you, okay? If you just remember what it is to be a log, okay, 3 to the power of something has to give you that value up there. That value can't be a negative number, okay? So just be aware of that, okay? So stick in your values and away you go. Show the function f of x is always increasing. Okay, as you can see, this thing is on the way up, but we need to be a little bit more rigorous than sure. Just doesn't it look like it's headed skywards and has no points of inflection. So this is of course to do with the slope. Now think what it means. Yeah, in fact, maybe just stop here for a second. Just have a think about what it means to be always increasing. What could you say about the slope if the thing is always increasing? So you're going to have to think about that. Maybe just pause the video for a second and have a think about it. Okay, if you were to take a function that's always increasing, what are you saying? You're really just saying that its slope is positive. Okay, even on something that's increasing like that, slope is a positive. If it does decrease at any stage, you're going to get a negative slope. So it's all about showing that the slope is always a positive number. What's our function? Our function is f of x equal to 3 to the power of x. So if we just go to our tables book, here's an example. You can see that we've got differentiation for a to the power of x is a to the power of x times ln a. So if we do f dash of x, or maybe just the slope, we're going to get 3 to the x and it's times ln a. That's ln 3 in this case. Right, is this always a positive number? Well, this thing here cannot be negative, as we know. So that's positive. This thing here is a positive number, so positive times a positive. So we can say that the slope is positive. Okay, that implies, or therefore, we can say f of x is always increasing. No inflection point, so we're going to have to double differentiate to get the double inflection point and let it equal to 0, except it shouldn't be possible for the thing to equal 0 is the whole point of it. So we're going to have to differentiate this again. So it's ln 3 times 3 to the power of x. So this can be a little bit scary to differentiate. Looks a bit scary, but really, you know, this is the same as having, you know, 5x to the 7 or something like that. The 5 just comes along. You would just get 7x to the power of 6 and multiply it by 5, as in 35 times that. So it's the same here. ln 3 does not have an x in it, just leave it alone. F double dash x is equal to ln 3 gets left alone. And actually, yeah, I mean, you can use the product rule, no problem, but no need to. So it's going to get multiplied by 3 to the power of x and again by ln 3. So what do we have here? We have ln 3 times ln 3, I suppose we'll call that ln 3 all squared times 3 to the x, 3 to the power of x, I should say. That's what f double dash x is. If it is an inflection point, okay, inflection point would imply that that thing, ln 3 squared times 3 to the x, would equal to 0. Okay, a consequence of that is you have something times something else equaling 0. Well, this thing is definitely not 0. Okay, that thing isn't. So it would follow that 3 to the x, 3 to the power of x is 0. That can't happen. Okay, there's no x value you can place in which is going to get you 0. We actually know that from our graph. If we go up there, as you can see, is the y value ever 0? No, this is heading there, and actually there's a technical word for that. This is an asymptote. Okay, it gets as close as you like to 0. We'll never actually reach 0. If you put in minus 100 or something like that, 3 to the power of minus 100, you're going to get 1 over 3 to the power of 100. You're going to get 1 over a gigantic number there. Okay, that's that one. Use your graph to estimate root 3. Well, what are we told? We're told f of x is 3 to the power of x. Now, how are we going to get root 3? Root 3 is 3 to the power of a half. So what we just have to do is we just have to make x equal to a half. Okay, so that implies x is equal to a half, and we want, and the result, the y value, will then be root 3. So you just go over to your graph, you go to x is equal to a half, and you read it off there. And I don't know what that is. That looks like 1.6, 1.7. I don't know. Just cheat. Stick it into your calculator so you know exactly what it is. But do dot it out on the here on the graph itself. If you don't dot that out, they will take marks away from you, because it does say use your graph to estimate it, and no, they are not so stupid as to think, oh yeah, that's fine. They have exactly the right answer to 9 decimal places. I bet they really read the graph very well there. They're of course going to figure that out. I don't know what the answer is. Actually, we might just have a quick little peek and have a look at Wolfram Alpha. And we'll just put in root 3. This is where having a calculator beside me would have been a better idea. And of course I've mistyped that in, obviously. So root 3, I do have a calculator here, and yeah, what do you know, it's 1.73. So we were pretty accurate. On that one. Okay. Yeah, stick with me. This is it's a long old video, I suppose, at this stage, but anyway, it's worth doing here. We have y is equal to ln of something. Find dy dx. You've got a couple of ways to do this. So maybe have a think about, is there some sort of smart little shortcut here that I wasn't really thinking of before I got nudged into it? And you should always have that approach to these things as you go along. Do we have St. Clair's things here? We do. And it does say stuff like, it says ln x is 1 over x. Of course, it's not quite ln x. There is a little bit more to it. But if you were just doing it the other way, you would just say 1 over whatever the thing is, x plus 1, and then you multiply by it differentiated. It differentiated is just 1. So you would just use the chain rule, it being x plus 1 differentiated. I should just make that nice and clear. So that's dy dx. So actually you don't really need to have a fast thing going on. You just have that nice and easy as we go along. So that's that one. Show that this is true here. So this is just a little bit of algebra. It's up to you which way you want to deal with it. It's a bit cheeky to multiply everything by x plus 1. What I much prefer, just a little classier thing, really is to start with one of the sides, like this one, and work it into the other side. So don't interact left and right, but you know, you probably get the marks for it. So you're going to need a common denominator. So 1 over 1, instead of writing 1 over 1, we'll write it as x plus 1 over x plus 1. That's being added to 2 over x plus 1. Now, a perfectly common denominator of x plus 1 at the top. What do we get? We get x plus 3 over x plus 1. So there you go. You have it, that those two things are equal to each other. And done. Hence, calculate this and the average value of that over that. So we'll do the average value in a second. So what they've done here is they've given you this, but you don't have the ability to solve this just straight off like it is. Now, I have to be honest with you, these papers were made quite a while ago. I'm not even too sure if they've kind of nicely given to you what it is. I'm not 100% sure that even this is on the course. I think it is. I'm going to tell you how to do it anyway, because you'll, I guess, need to know it for college. Just make sure there's a little dx around it, and that's 1 and 3. Okay, for this thing here, it's helpful to know a little bit of extra integration, which I'm just going to give to you now. Okay, and here it is. It says that if you have the integral of 1 over ax plus b. So if you've got a linear function, okay, 1 over a linear function, you're going to get 1 over a ln ax plus b, and obviously there's a plus c that goes in the end there. Now have a little look at what we have here. We have the integral of 1 plus something. So we can break this thing up, okay? And I will. Because you've got something plus something, you can do each one individually as you go along. So 1 to 3 of 1, that's dx, plus integral from 1 to 3 of 2 over x plus 1. Now, a better way to think about this is, remember what our thing over to the right hand side is it's 1 over something. So instead, if you write it as 2 times 1 over x plus 1, that's going to be much more helpful. Okay, so it's 2 over 1 times that. And in fact, you can go from 1 to 3 of 1. Remember, we haven't actually integrated anything yet. If you have just a number times it, that's fine. You can just take the number out and go from there. 1 over x plus 1. So if we just use this thing here, the integral of 1 over x plus 1, I think you can see what it's going to be. A is 1, b is 1. So it's 1 over a, 1 over 1. And it's ln of ax plus b, so that is x plus 1. So that is what we have going on there. So let's just do it. We are going to integrate 1, which is going to be x, and we're going to do that from 1 to 3. And added that is going to be 2 amounts of, and we're going to have 1 over 1, that's just 1, so it's just ln x plus 1. And again, we're going from 1 to 3. Okay, place 3 in, and then place 1 in, subtract them. Okay, that's going to be that one. And we're going to do plus here. And you know, maybe we should have done it a different way, I don't know. But if we do it like that, I'm just looking ahead at what it's going to be. But it's going to be the ln of, and what you should do is you should place in 3. That's going to give us ln 4. And it's going to be minus, and you place in 1, and it's going to be ln 2. So what are we going to end up with? We're going to end up with 2. Added to 2 amounts of. Now we have ln 4 minus ln 2. You might remember ln a minus ln b is equal to ln of a over b. So that's 4 divided by 2, which is 2. And there you have it. What am I forgetting? Nothing. 2 plus 2 ln 2. Okay, you can factorize out of 2 if you want. That's evaluating it. To get the average value, you would have done 1 over b minus a of the exact same thing. So it goes from a to b. So it is going to be 1 over 3 minus 1. And I would show that little calculation, just show the examiner. I know what I'm talking about. It's 2 ln 2. So it's a half of this thing. So it's just 1 plus ln 2. Okay, that is your average value from 1 to 3. This was evaluating our previous answer, and this was our one. So just make that nice and clear. That's that one, and this one here is our average value. Okay, this is the last one that we'll do here. Is this a continuous function? This is also a new thing for you. So it actually does tie in a little bit with injective, surjective, bijective. In order to be a continuous function, what it means is you have to be able to, at all times, keep your pen on the page as you draw the thing. Okay, if you want an example of something that isn't a continuous function, I will give you an example. We'll take 1 over x because we used that one before. Basically what we want is, in order to be not continuous, you want to have a value that you cannot put in. Okay, so in order to be continuous, you have to be able to put in anything. So example of continuous function, y equals x. There is every single x value. You can put in this x value, get y that y value. There's every x value. You can place in that one, you'll get that y value, etc. But what would this thing look like? Okay, as I place in, let's say, here's my y value, here's my x value. Let's say I place in 1, x value of 1. I'm going to get a y value of 1. But when I place in 2, I'm going to get a half. When I place in 3, I'm going to get a third. When I place in 4, I'm going to get a quarter. Now, if you can see what's going to happen here, you know, let's say I put in 100. It's going to be just above the line, okay, way close to the line there. But my point is this, if you'll excuse the pun, this thing here is never going to reach 0. Okay, if you put in 1,000,000, you'll have 1,000,000th. It'll be very close to 0 on the y-axis, but it won't be that on the y-axis. Now, what if I put in a half? Think about that one for a second. If I place a half in for x, what am I going to get? And hopefully you said 2. If I go a little bit closer, if I go to a quarter and I place that in, I'm going to get 4. So this thing here is actually on the way up. Now if I put in like 1,000,000th, I'm going to get 1,000,000. So again, this thing here, it's going to go all the way up. And it's going to get as close to an x value of 0, but you won't actually be able to put in an x value of 0. And I think you can see that already. So you actually won't get that value here. So this is what we were talking about beforehand. This is an asymptote. It's an asymptote to two things. It's an asymptote to that line there. Okay, it's an asymptote to the x-axis. It can get as close to the x-axis as it like, but it will never actually hit it. And it is also an asymptote to the y-axis. Okay. You will get as close as you like to the x value being 0, but you will never actually hit that value at all. Now, what's the point here? The point is, let's place in -1. You place in -1, you are going to, for x, you're going to get a y value of -1. So it does that again. If you go and place in a value of -2, you get -1/2, -3, -1/3, etc. So the same thing happens over here. And if you place in -1/2, you get -2. If you place in -1/4, you get -4. It does that thing there. Why is it discontinuous? Because if I were to draw a line going from left to right, obviously I would start at, over -infinity. But you can see here that I'm going to have my line go here. It's going to go all the way to -infinity. And there is a disconnect at x equals 0 before I come back over that line there. So is this thing continuous? To cut a very long story short, the answer is no. I would have had to lift my pen in order to draw from left to right. So no, because, should explain it, and it does say it there, because x can, well, sorry, yeah, this is a different function than the one that we're dealing with. Is there a particular x value that we cannot input? And this is where there is going to be an asymptote in this case. Is there a value that we cannot put in? And there is a value that we can't put in because x cannot equal to -1. So how do you cheat on this? You cheat by going to the bottom here and you say, okay, there's a value there that you cannot put in. Okay, you can put in either side of it. That's important. Can I put in, -2? Can I put in 0? The answer is yes. I can do both of those things. I just can't put in -1. Okay, so there is obviously a break in the connection of the line between the two things there. So that is what it means to be a continuous function. Okay, look, there was an awful lot in this. I would really take my time and study this video, go back over it, because the topics are not so easy. The thing I want you to do, so I want you to have a little go at this injective, surjective, injective, bijective question right here, and I'll make a video out for it. Some of you very kindly emailed me asking specific questions. I'm going to make a video of those specific questions. Thank you very much for getting in touch with those. I'll be more than happy to do those, and I will chat to you again. Thanks a million, gents. All the best.